Welcome back. In the previous video we have discussed various parameters like the global horizontal irradiance, diffuse irradiance and the direct irradiance. In this video lecture we will discuss how much irradiance is incident on a PV module depending on its orientation. The learning objective of this video is to calculate the irradiance on a PV module based on an angle of incidence determined by the sun position and the module orientation and the global, diffuse and albedo irradiance components of the sunlight. To calculate how much irradiance is incident on a PV module, we have to define the position of the module in reference to the sun. Let's start with the position of the sun. Since celestial objects like the sun, the moon and the stars are very far away from the Earth, it's convenient to describe their motion projected on a sphere with arbitrary radius and concentric to the Earth. It's very important to note that because of the distance of celestial objects in general and the sun in particular being much larger than the radius of the Earth, we can consider the observer and the center of the Earth coincident. This sphere is called the celestial sphere, and this point is the position of the celestial object. For photovoltaic applications, it is most convenient to use the horizontal coordinate system where the horizon of the observer constitutes the fundamental plane. In this case, the horizon of the observer is the gray area beneath the hemisphere, and on the left side you can see the representation of a plane tangent to the Earth, where the blue dot is the observer. Another important thing to realize is that your module now becomes the observer. Therefore, the celestial sphere will have the same inclination as this plane. As I anticipated, we may neglect the translational shift of the origin of the coordinate systems from the observer to the center of the Earth, and thus if the PV module now is the observer, we can always find the position of the sun in terms of two angles. The altitude A, which is the angular elevation of the center of the solar disk above the horizontal plane. Its angular range is between -90 to 90 degrees, where negative angles corresponds to the sun being below the horizon and which corresponds to the time during night. The azimuth A is the angle between the line of sight projected on the horizontal plane and the north. It's counted eastwards such that north has an azimuth of 0 degrees, east of 90 degrees, south of 180 degrees and finally west of 270 degrees. Its angular range is between 0 and 360 degrees, but note that different conventions are also used by the PV community. For example, the south might correspond to 0 degrees and angles are counter westward. To be clear, from now on we will use only the convention where A is 0 corresponds to the north. This is two sets of coordinates. Azimuth and altitude of the sun with respect to the observer is very important because they are the input parameters to calculate the solar position in the sky at a certain time and date. As mentioned, you could simply place a PV module flat on ground. In that case, only one component of the global radiance is enhanced. For a horizontally inclined module, the diffuse component is increased because the module can receive light from the entire hemisphere. Let's have a look at the system that we would like to optimize. Here we have a solar module mounted on a plane, tilted at a certain angle theta m. The irradiance that is incident on the module can be divided into three components. The direct irradiance is directly incident on the module. The diffuse irradiance is the solar radiation that reaches the module surface after being scattered by the molecules in the atmosphere. Finally, the albedo is the part of irradiance that reaches the module after reflection by the ground or objects in the neighborhood. To determine these components, we have to define the orientation of the module in reference to the horizontal plane of the observer. In this picture, our PV module is tilted with respect to the ground and at an angle of theta m. Here we can describe the position of the module according to its normal vector, which the one highlighted in red that identifies a point in the celestial sphere. This point can be located in the horizontal coordinate system by means of two coordinates. First, we need the azimuth of the module, which is the angle between the true north and the normal of the module projected on the horizontal plane. Be careful to not confuse azimuth of the module with the azimuth of the sun. The second coordinate we need is the altitude of the module, which is the complementary angle of the module's tilt as written in the equation. Now let's have a look at the angle of incidence. The angle of incidence is the angle between the module normal, depicted by the dashed green line, and the incident direction of the sunlight, represented by the red beam. So we indicate the angle of incidence in this figure in red. In the top of the slide you can find the trigonometrical equation used to derive the angle of incidence. You can see that it is only a function of the azimuth and the altitude of the module normal and the sun position. The derivation of this equation can be found in, for instance, the solar energy book from the Delft University of Technology. It is important to realize that this drawing is in two dimensions. This means that the angle of incidence highlighted in the red is true only in case the azimuth of the module corresponds to the azimuth of the sun. Now we have all tools to divide the incident irradiance into three components we introduced earlier. The direct component can be calculated using the following equation. We can notice that the direct irradiance component is proportional to the direct normal irradiance, or DNI, times the cosine of the angle of incidence, which we have just derived. The other component that contributes to the incident global irradiance is the diffuse component. There's not a single unique equation to obtain diffuse irradiance. The calculation of the diffuse irradiance depends on the sky model that you want to use. Sky models differ in complexity, but in general they are a function of the diffuse horizontal irradiance, the angle of incidence, and most important, the sky view factor. This parameter only depends on the tilting of the module, and it represents the portion of the sky seen by the module. As the tilt angle increases, the portion of the sky that the module faces decreases. For example, when the tilt is 90 degrees, then only half of the sky irradiance can be received by the module, and indeed the cosine 90 is 0 and the equation gives 0.5. Therefore, when the module is flat on the ground, light is incident on the module from the entire hemisphere. On the other hand, when the module is tilted, in order to optimize the direct irradiance, the angle from which light can be reached the module is limited, and therefore the sky view factor has to be calculated. The last component that makes the irradiance incident on the module is the albedo. The module receives radiation that is reflected from the ground and the surrounding environment, which can be approximated by this equation. GHI, as we have already seen, is the global horizontal irradiance, and alpha is the albedo coefficient, which expresses the reflection from the ground and the environment. The lower the albedo, the more light is absorbed by the ground and the environment. For example, the albedo of vegetation is around 25% or 0.25. That of snow is around 0.6 or 60%. The albedo of an urban area is between 0.05 and 0.4. The albedo of water is merely around 0.1. The albedo can be measured with an albedometer. This consists in a pair of pyranometers mounted parallel to the ground, one pointing downwards to measure the intensity of reflected light from the ground, and one pointing upwards to measure the GHI. The ratio between these two quantities is the coefficient alpha. In addition, the albedo component becomes smaller when the sky view factor of the module becomes larger. In summary, Summary. We divided the irradiance incident on the surface of a module into 3 components. The direct irradiance can be calculated by multiplying direct normal irradiance by the cosine of the angle of incidence. The latter was derived using trigonometry. The second component is the diffuse irradiance, which depends on your choice of sky model and the available measurements. Generally, the diffuse irradiance is a function of the sky view factor, the DHI, and again the angle of incidence. The third component is the albedo, and it depends on the global horizontal irradiance, the albedo value of the surrounding ground, and again the sky view factor. The formula to compute this factor depends only on the tilt angle of the module, and it is necessary to obtain the diffuse and albedo components. In the next video we will discuss how to find the optimal tilt angle and how sun tracking methods can enhance the yield of PV systems. So, see you back in the next video.